So next and last paper will be about sampling-based training criteria for neural language modeling, and it will be presented by Yingbo
Gao.
Sorry.
Yeah, thank you.
From Aachen University.
Yeah, thank you. Welcome. My name is Yingbo Gao. My colleagues and friends also call me Ringo. I come from RWTH Aachen University, so I'm supervised by Professor Nai, who's also sitting here, kindly chairing this session with Ms. Elina. Thank you. I'm also affiliated with Aptec GmbH in Germany, so let's jump into this talk. The agenda for my talk today is first talk about a problem with word-based language modeling and what motivates us to do this work. Then I'll walk you through 3 traditional training criteria to further motivate the sampling-based training criteria. And finally, we'll look at the experiments and conclusion. So first, problem and motivation. So one problem with word-based language models nowadays is that the vocabulary size is getting larger and larger. So typically for a commercial system, it's not uncommon to see vocab sizes of several hundred thousands to even millions. And because normally we do a softmax to get the normalized probability output, that means we have to inevitably traverse over the full vocabulary to do the denominator. And this means inefficiencies during both training and inference or testing. And to solve this problem, one of the most prominent methods is called noise contrastive estimation, or in short, NCE. It was originally proposed more than 10 years ago and later adapted for language modeling, and ever since has been the prominent method to do sampling-based training. And its self-normalization property has also been discussed in literature. More recently, the method is also adapted for general representation learning. Essentially, NCE, what it does is that it changes the 1 in C classification task to a binary classification task where the model is asked to tell true samples from noisy ones. Since NCE is so prominent, a natural question is to ask is what about the other sampling-based methods? Because we have to know that not all competing methods guarantee this self-normalization. And actually, in a preprint note by Chris Dyer, he actually wrote, if your goal is language modeling, you should use NCE. And if your goal is word representation learning, you should consider both NCE and negative sampling. So as a result, one may have this impression that NCE is so much more superior than the rest of the methods, and the other methods may be overlooked. Our motivation here is that we look at several of these sampling-based training criteria, and we notice a one-to-one mapping between the derived model optimum and the intended posterior. So a natural question to ask then is, what if we correct for the intended posterior? Would that mean that all of the sampling-based methods would perform equally well? Having that question in mind, let's move on to the next section where I talk about 3 traditional training criteria, and the first one being mean squared error. So here a little bit on the notation. F is something we want to maximize, and or small n is a running index in the total number of positions. C is a running index in the total number of vocab size. Xn is the context. So in the case of autoregressive language modeling, that would be the words to the left side beginning of the sentence or the left side context. C is the word we care about, and that's the Kronecker delta we're looking at. Nicely, we know that the model optimum for mean squared error is exactly at the model at the posterior we want, or the empirical posterior we want, which is nice. Intuitively, because we do this squared error, it's kind of like counting the errors, but in a continuous sense. A note on the Q, so this Q is the model output. It doesn't have to be bounded, but further activating it with a sigmoid activation helps a little bit. Actually, recently there's a paper which discusses and saying that mean squared error should be preferred over cross-entropy. Or in our case, that's not really true in our experiments, and we contribute that to the fact that for word-based language models, the vocab size is much, much larger than what's considered in that paper. Okay, let's move on to the next one, binary cross-entropy. This is also a very classic one. From the surface form, essentially we have a log Q term and a summation over the rival terms, which is the log 1 minus Q terms. And also nicely, we have exactly the model optimum at the posterior. It's nice to have, so we can, of course, use this criterion to train pretty good baselines. Here, the Q should be bounded between 0 and 1 because Q, or the model output, shows up both in the log Q and log minus Q. So by definition, it should be bounded. And in reality, using sigmoid activation also is very common. Moving on to cross-entropy, this way of formulating it is probably not very familiar because we explicitly write out the softmax function, and if you recall, a log of exponential cancels, so that's why we have the first term q, and the second term log sum of exponential, that's the denominator term in the softmax function. By writing the softmax explicitly out, we can see the summation over c down below. In this case, the optimum is the softmax output, so as we all know, it's also nice and also the reason why in reality we commonly use cross-entropy. Now, having looked at three traditional criteria, we quickly realize what the problem is, because in all three cases, we see this summation over C. And this summation, keep in mind, it's in several hundred thousands or even millions. It's really inefficient. So let's move on to the sampling-based one. We saw that the summation over C is common for all three traditional criteria, and we can think of it as an expectation of some quantity QC because we can do a simple rewrite, and that's the expectation under the uniform distribution. And the core concept of doing sampling is basically to approximate this expectation. In our work, we considered 4 variants of sampling, namely Monocolor sampling, importance sampling, and something we call compensated partial summation, which we'll talk in a bit, and also NCE for all three traditional ones. So in total, that makes 4 plus 1 and times 3. In total, 15 training criteria. But of course, due to the time constraint here, I'll only talk about 4 of them, which is the BCE variants. Also in literature, sometimes you see methods like self-normalization or variance regularization. These methods, they only speed up testing because in training, they still have to go over the full vocabulary to calculate the normalization term or the variance term, and we don't consider those methods here. Okay, so we said we want to look at 4 variants of BCE-based sampling. So the first one is Monocolor sampling. We quickly realized the difference to the binary cross-entropy case is that the second summation over the rival terms is simplified. Now we only sum over k noisy samples, and these samples are drawn from some noisy distribution, which is denoted by D in our case. So we did the math, and the optimum is shown as on the screen or here. Again, we don't have this nice property that Q is exactly P anymore. However, it's pretty straightforward that Q and P has a one-to-one mapping, which means we can write P in terms of Q, and that's the core motivation of this work, basically. In literature, negative sampling is one of the most prominent examples of Monocolor sampling. The next one is called importance sampling, and the difference to the Monocolor sampling is basically we use this KD term in the log 1 minus Q terms. And here, again, we derive, and it's not on P, but one-to-one mapping is there, which is nice. Moving on is this compensated partial summation, which we call it like that. And the motivation is really simple. Originally, we had a summation over C terms. Now we're replacing it with K terms. And naively, maybe we should divide by k and then multiply c back to compensate this difference. However, this is naive because you can think of a simple example. You have 3 terms added up, 1, 2, 3, and you sample 1 out and you multiply 3, you get 3 instead of 6. So this is only hold true when all of the items are the same, but nonetheless we implement and test this one. And the model optimum is also shown on screen here. And finally, NCE, or noise contrastive estimation, which was the prominent method. So from the surface form, it's actually very similar to Brownian cross-entropy. The difference is that what enters the log and log 1 minus calculation is not directly the model outcome, model output, but this term Q over Q plus KD. So essentially, Q is the true sample and KD are the noisy samples. So this is why we say it's a binary task where we have to tell the true sample from the noisy ones. And here we see that nicely the model optimum is exactly at the posterior, and this is also the reason why people prefer it in reality to use NCE. So we talked about 4 criterion, and we list all of the optimums here, and we quickly see this argument that one-to-one mapping is existent for all cases, and BCE, NCE is nice because you exactly have the posterior, but nonetheless you can correct for the posterior. So recall we had this question, if we correct, what would happen? We think they should behave exactly the same, and then we can look at these experimental results. So for experiments, we consider 2 standard tasks, Switchboard and LibriSpeech. On the slide here now, you're looking at the first pass results. The language model is 4-gram and LSTM respectively. These are rather competitive models, or it serves the purpose of being the baseline for this task. And here what's shown is the results for Switchboard. Because our purpose is to see if there's a difference among these sampling-based methods, and not really to find the best number of samples or the best noisy distribution. That's why we don't really sweep over the k values or the noise distribution. We set k to be 8,000 and use the Zipfian noise distribution. First thing you notice from this table is that the baseline with no sampling is improved. That's because in the second pass rescoring, a better language model is used. Second thing about this table is that if we look at the training time, we do see the expected speed up across the board. There's no big difference among the methods. And finally, if we look at perplexity and word error rates, there's virtually no difference. Probably you can say 49.9 is better, but that's a model that's been tuned for a long time on Switchboard. And if we move on to LibriSpeech, the message is also there. Across the board, we have 40% relatively speed up now because we're sampling 8K out of 200,000 instead of 8K out of 30,000. And if we look at the perplexity and word error rate, there's no reason to say NCE should be preferred over the other methods, or at least from the perplexity and word error rate point of view. Finally, the most interesting thing about these sampling-based criteria is the self-normalization property, because in testing, you can hope that the model is self-normalized and directly use the scores as if they are probabilities. In this case, we also did this experiment on Switchboard, and as you can see, the important sampling case is exactly performing the same as NCE. The other two are worse because if you recall, we had to query the unreliable noise distribution when we correct for the posterior. Okay, that's pretty much all. So in this talk, I gave you this impression that NCE was prominent. Hopefully you agree. And we noticed a one-to-one mapping between the model optimum and the expected or the intended posterior for all of the sampling-based training criteria we considered. And we say if we correct for the posterior, we should get similar performance. And with word error rates and perplexity, we can show that. Okay, that's all. Thank you very much for your attention, and I'll be happy to take questions.
Thank you very much. Do you have any questions, comments? No, no questions. I have one question. Yeah. In your article, you talked about free learning criteria. Okay.
Free
learning criteria.
Okay.
Mean square error, binary cross-entropy and cross-entropy. Okay. Could you say a few words about why you did not present the results for mean square error?
Okay, so actually in our early work, we spent a lot of time to tune this mean squared error model, and we tried to even load a converged model that was trained with cross-entropy or binary cross-entropy and really use really small learning rates. But the experience is whenever we start to train with this criteria, the model starts to diverge and the perplexity gets much worse. There is one thing that helps. So we already said that activating with sigma helps, right? There is one thing that helps is we see there's a summation over C for mean squared error, right? So you can single out the term for the correct class and the rest of the rival terms. And if you downscale the sum of the rival terms, you still gain, you can see a little bit of improvement. But if you compare that with cross-entropy and binary cross-entropy, it's still far away. So that's why we don't talk about the results there.
Okay,
yeah.
Thank you. More questions? No? I have one more question.
Yeah.
It's more general question,
Mm-hmm.
and I am interested by your response. Mm-hmm. In your system, you do not use positional encoding. Can you tell us why?
Positional encoding, as in transformer? Yes. Okay, so we worked on two data sets, right? One Switchboard, one LibriSpeech. The Switchboard models, they are LSTM models. So these ones, because LSTM implicitly we have the recurrences, so we don't need position encoding. For which one? Yeah, for LibriSpeech, these are transformer-based language models. I have to check with my colleagues who actually ran some of these experiments. But I think there is a work by our former colleague Kazuki Iri. In his work, he said that for transformer language models, because the way you feed the data into the network is always giving the previous words you want to predict the next word. So the vector you query with is always the previous word, and we know the previous word is the most important word to get the posterior. He finds that if you don't use positional encoding, you can also gain similar performance. But in our case, if we actually include it, I have to check with my colleague. Yeah.
Okay. Okay. Thank you.
Thanks.
I think maybe yes.
Channel channel, I should say. There seem to be questions about the morphology of the language. Any idea to what degree the morphology or the richness of the morphology of the language matters?
Okay, so I have to speculate because that was not the main focus of the work. From our experiments, as you see, we have two experiments with the vocabulary size being 30K and 200K. Although it's always English, my guess would be it's probably more related to the size of your vocabulary and the distribution of your words more than the language itself. That would be my guess.
Okay. That's it. No more questions?
Yeah, okay, cool. Thank you.
Okay, thank you. Thank you
That's
very
it
much.
for today. Thank you.